So the second part of the video on concave, convex and points of inflection is on points of inflection because we managed to do concave and convex earlier. So point of inflection, you need to write down a sort of definition. So a point of inflection is where the curve changes between convex and concave. Okay, could be the other way around. Oh, convex. Okay, it could be the other way around. So it could change between concave and convex. That's going to annoy me now. That does say convex. Okay, so that's what the definition is. A point of inflection is where the curve changes between convex and concave. So we can see in the graph on the left, we have y equals x cubed. So here, it's starting to concave, but then over here, is starting to convex. So in the middle somewhere is a point of inflection. Over here, this part of the graph is concave, and here, this part is convex. Okay, so somewhere in the middle, there must be a point of inflection where it changes between the two. Okay, so I'm going to use some colours to help kind of show you. So over here, where we've got our sort of concave shape, we know that when a graph is concave, we know that the second derivative is less than 0. And then when we've got our convex shape down here, we know that the second derivative is greater than 0. So up here it's less than 0, so it's negative, and down here it's positive, it's greater than 0. So that means that somewhere in between something must have happened, and it must have changed from negative to positive. So at some point it must have been equal to 0. Our second derivative must have been equal to 0 at some point between the two. Okay, so we know at a point of inflection, our second derivative is equal to 0. Okay, so we know that at some point in between our concave and our convex, that our second derivative was equal to 0 at a point. So we're going to just kind of quickly go through how you'd find your point of inflection for y equals x cubed, even though you can probably guess where it's going to be for this one, and where you can find your point of inflection for y equals x cubed, take 5x squared. So to find your point of inflection for y equals x cubed, we know that our second derivative, we're going to set it equal to 0. Okay, and if I solve for x, I can see that x is equal to 0. Okay, so we know what the graph of y equals x cubed looks like, so we know that that's definitely a point of inflection. Okay, and then we're going to do y equals x cubed, take 5x squared. So find our derivative and our second derivative. Set it equal to 0. So we know that 6x must equal 10. So that means x is equal to 5 over 3. So we can see on the graph, this is the point 5, because I can factorise it, y equals x squared brackets x take 5. So I know that that point is 5. So we can see that that's about right, that this point here would be that x is 5 over 3. Okay, it looks appropriate. But there's something that we also need to consider. So the graph of y equals x to the power of 4, okay, that looks like this, something like that. Okay, if we were to find our derivative, 4x cubed, and our second derivative, and set it equal to 0, well, here we've only got a convex. X to the power of 4 is only a convex graph, that's it. There's no concave as well, so there shouldn't be any points of inflection. But when we say this, when we solve it, we get that x equals 0 as a point of inflection. Okay, so that leads to something really important. So earlier we said at a point of inflection the second derivative equals 0, which is correct. Okay, so I'm going to rewrite it. At a point of inflection, our second derivative is equal to 0, but not all points where the second derivative equals 0 are points of inflection. As we've just seen, the second derivative is equal to 0 when x is equal to 0, but that's not a point of inflection. So just because our second derivative is equal to 0, it doesn't mean it's a point of inflection. So when that happens, so with a point of inflection, we need to check what's happening either side. So we need to check, I will show you what I mean in a second, is happening either side of a point to see if it is a point of inflection. Or not. So it could be a minimum or a maximum point instead. Like this one, we can see that we had a minimum point there. It flagged it up that second differential is equal to 0, but it gave us a minimum point. So just because that's the point where the second derivative is equal to 0 doesn't mean it's a point of inflection. So what we need to do with something like this, so with our graph from earlier, we found that that was x equals 5 over 3. We check what our second derivative is this side of 5 over 3. We check what our second derivative is this side of 5 over 3, and we could see that this side it would be negative, this side it would be positive, so I know that that's a point of inflection. Again, the same here. I would know that this side, the second derivative, would be negative, and this side, I would know that the second derivative would be positive, so I know that's a point of inflection. Whereas here, if I check this side, my second derivative is greater than 0. If I check this side, my second derivative, this side, is also greater than 0. There's no change in sign, so that's definitely not a point of inflection. So I go through another example on one of the next videos, so make sure you kind of write it down. I've got some points here that I'd recommend you write down on convex, concave and points of inflection. So I will pause it to write down some notes. So there's the convex and concave, and there's our point of inflection. So we've got here that sometimes it's at a stationary point, not all the time. Okay, it doesn't really help us. So here we can see that that point of inflection is at a stationary point because the gradient's 0 momentarily, and here that's not at a stationary point. Okay, so this is important. It's only sometimes at a stationary point, where the curve changes between concave and convex. At a point of inflection, our second derivative is equal to 0, but not all points where this is true are points of inflection. We need to check what's happening either side of a point to see if it is a point of inflection or not.